Yeah. Okay. How do I get this out? Okay, let's begin. Is it visible to you guys? Readable, right? Okay. Yeah. Okay, so in the last class we were looking at the noise in a MOSFET and the notion of the input referred noise. So first I'll give a quick recap of that. So we know that if you have a resistor, the noise generated by the resistor can be modeled using a parallel current source with a power spectral density 4 kT by R, right? Similarly, for a MOSFET, the thermal noise in the drain current can be modeled using a parallel current source 4 kT gamma GM with this power spectral density. Now with a MOSFET, along with this thermal noise, we also have the flicker noise, which can also be modeled as another current source, and its power spectral density is inversely proportional to frequency. Okay. And as I mentioned, thermal noise is a more fundamental phenomenon arising due to thermal energy, whereas flicker noise is coming due to the imperfections or impurities in the fabrication. So the flicker noise is heavily process dependent. Okay. And we saw if we have any circuit with a lot of such noisy components, we can find the total at the output. We can find the power spectral density for the, say, the voltage or the short circuit current, and we do that by considering each noise source one at a time. So you take the kth noise source, it has, say, power spectral density, say Sk of f. You find the transfer function from that noise source to the output, that is, say, some Hk of f. You take magnitude square and do it for all noise sources. Okay. But let me write it. But we saw that this, oops, how do I get rid of this? Yeah, we saw that if we looking at the output noise is not a great measure to compare different circuits. So we decided that instead of looking at the power spectral density at the output, we model the noise generated in the network, assuming that the network is noiseless. So this was a noisy network. So basically we assume that there is no noise coming from the resistors or the MOSFETs, but the entire noise is generated due to an input voltage source. Okay. And this was the input referred voltage noise we called VN. Okay. Great. But we saw that this is not great in all cases, especially because finally we are going to connect some input here, and that input voltage can have some source resistance. Okay. So now if we have to find the noise contribution, we say the input is 0, so this goes off. But if the input resistance of this guy is small enough, it appears as though only a small fraction of this noise voltage is fed into the network and the output noise is very small. But that's obviously not the case. The network is generating the same amount of noise irrespective of the source resistance. The issue is coming because we are trying to model the noise in the output using something at the input, and obviously this voltage source alone is not enough. So what did we do? We also told we need a current source, and I call that IN in. Now both of these together capture the effect of the noise, so that irrespective of the source resistance you get the same total noise at the output. Okay. And one thing is, see, both this voltage and the current noise, they capture the effect of noise of the same network. So do you think they will be correlated or uncorrelated? Correlated. They will be highly correlated. Okay. So I will probably write it somewhere here. VN in and IN in, they will be highly correlated. And here you can see if RS is 0, the noise is coming only due to the voltage, so we get only Vn in. So that gives an idea as to how we can find the value of this input referred voltage noise. You take that Rs is 0, so that simply boils down to shorting the input port. So we'll short the input, and then in the network you find the total noise in the output current like this, and then you find the transfer function from the voltage noise to the output current here. Say it has some y of f, and then you can find S Vn in of f to be S I out of f by mod y of f square. Okay. Now similarly, if you want to find the input referred noise current, what do? Yeah, the entire noise will come from the noise current if you have Rs to be infinity. That boils down to saying that we are opening the input port. I mean, one thing to notice, the input source is always 0. We are not applying external input, but we are only making the Rs to be 0 or infinity. Okay. And that translates to opening or shorting the input port. That's all. So here you do the same thing. Finish this. You open this guy and then do all the calculations. So now if I make Rs to be infinity, I'll have noise only due to the noise current. So now I'll find the transfer function from the noise current to the output current. Say from here to here, this is say some h of f. So you find the path spectral density by the same thing. Okay. And one other thing is, if the input impedance of the network is infinity, you don't need both voltage and the noise. Voltage is enough. So the input referred noise current will go to 0. Okay. And that's simply because, I mean, the entire noise at the output you can capture only using the voltage. And in fact, the need for this current source came about because the input impedance was finite. So if it's infinite, the noise itself can model the total noise. So the current is 0. Great. So then we looked at a few examples, and I also gave something for you to guys to work out. I'm sure you didn't do it. So why don't you do it now? So let me draw the circuit again. Think this was it. This is RF and RD. V in and V out. Okay, I'll pause this guy and okay. And by the way, do you recognize the circuit? Or let's say if I slightly modify it. Say this, oops. Let's say this is RS and RF, I ignore RD. If this is V in and this is V out, what do you think the approximate gain of this will be, V out by V in? Any guesses? Huh? Take some guess, right? Yeah, why? At least from a long distance it looks like an inverting amplifier, and it is indeed an inverting amplifier, right? See, one simple thing is, if let us say the transistor is all ideal, right? R0 is infinity and even GM tends to infinity. If GM is infinity, what can I say about the gate to source voltage? It has to be 0 if the voltages are all finite. Okay. If the gate voltage is 0, I mean VGS is 0, this. So then you have a very similar case like you have in an inverting amp. So the current flowing through it, this is V in by RS. Same current flows here and generates the voltage. Okay. And of course, if you have finite GMs and or not, things will be different. And in fact, in this circuit, if you have a finite GM, if let us say this is some VG, from the input to the output, do you see that, I mean, are there multiple paths? Is there multiple path for the current to flow from input to the output? Huh? This is, I mean, let's say consider VG as the input for now, right? You see that you have a path from this guy and also a GM VGS coming here. And if you look at the signs of the things, right? So what is the current flowing through the resistor RF? Let us say I'll have to mark the direction. Hold on. Let me mark all the currents flowing into the output. So what is the current through RF? VG by RF. Yeah, I mean short circuit current, let's say. Or even if you don't short circuit, it's okay. It's VG minus V. Okay, let's short circuit it for simplicity. This VG by RF. What is the current entering here from the transistor? Okay. You see that these two have different polarities. So if we choose this to be the case, you will need get the output to be 0. Okay. I mean, this was again similar to one of the quiz questions I gave, right? You had something like this. So essentially, I'm redrawing the same thing again and again. Okay. And yeah, and this is actually, I mean, one difference from VCCS and the VCVS, right? See, let us say this transistor here, as such, didn't have any R0. Then what is the intrinsic gain of this guy? It has, let's say, finite GM and infinite R0. Gain is actually infinity. Okay, but even though the gain of the transistor itself is infinity, this is a VCCS, so I'll model it like this. The moment I put it in feedback like this, now we see that the gain is kind of finite, right? Because now the gain depends on what I'm connecting here also. So if you try to find the loop gain here, let's say, oops. Okay, and this is, let us say, some finite GM. What do you think? What do you think will be the loop gain? I mean, I can break the loop. So where can I break the loop? Usually break it at the input of gate. And if you have multiple transistors, choose a transistor which has the smallest gate capacitance. Okay. If I break it here and apply some test voltage, so what do you think will happen to this voltage? This is pumping in a current, I mean minus GMV test. That current flows into this, and this is okay. So the only way to make loop gain infinity is to have GM to be infinity. Only then you can get an ideal inverting amplifier. But that's not the case if you have a VCVS. If you let us say have a voltage controlled voltage source that has an infinite gain to start with, doesn't matter what I connect it across it, it will maintain infinite gain. Okay, anyways, that is aside. Yeah, so hopefully now you get the hang of how to do this noise calculations. And actually, if you think carefully, in all our amplifiers and in all our op amps, the input is actually given to the gate of some transistor, right? This is where I apply the input, and let's say have the rest of my circuitry here. This is my output. So for these amplifiers, if I were to model the input referred noise, is there anything you can say? I mean, for modeling noise, I mean, to find the input referred noise, how many things I need? No. Voltage, and we need both Vn in and In in. So can you comment anything here? Current is not needed, because the input here is basically gate of a transistor. So as long as I don't consider the gate capacitance, I actually don't need this guy. So only input referred voltage noise is sufficient to model my output noise. in all our amplifiers. Okay. And now things becomes easy for you. For finding the noise, you just need to short the input port, find the total noise either in the voltage or current, and then find the transfer function from voltage to current, and then it's all set. Just one quantity you need. Okay, so let's do one more example to get something. So let's say take this. See, this is V in, V out, D and RS. Okay. So here, let's say I'm interested to find the input referred noise. Again, what can you say about the current? We don't need the current for modeling the noise, so only voltage. So can you help me find this? Again, so the last thing pending is to find the current due to the transistor. So let's do that. So let's say I use this guy, or I'll do it separately. Let's say do it here. It's okay. Yeah, I'll call it say IN of transistor M. See, in this, I mean, you can do it multiple ways, but there is one trick which I like it. See, let's say in any circuit, if you have a current source I between nodes A and B, okay, I can split it into two current sources like this, each having the same current value, nothing changes. And what can you say about this potential? We cannot say it can be anything in the world. So if it can be anything in the world, what can you choose it to be for your convenience? 0. Okay. So basically now I can say that I have a case like this. Right. So for all that matters, I see in the original circuit I had a current I being pulled out of the node A. I have the same scenario here. On the other side, I have the current I being pushed into the node B. I have the same thing. Okay. So this actually makes it easy for you to analyze noise contribution due to such floating current sources. So let's do it here. This is RD, this is ground. So what I'm going to do is this single current source, I'll split it into two. Okay, and of course the output is short circuited. Let me make that. So let's say I now split it into two, or I'll draw it like this. Ground. Okay, this is, let us say, INM and INM. Is that okay? Yes, sir. So now you see that this current which I have drawn in green is very similar to the current we had for the resistor, RD resistor, and the current source here does something similar to what happened for the noise current of RS. That makes it easy for you to analyze. But the one main difference is here these two current sources were uncorrelated, but these two are exactly correlated, 100% correlated. Okay, so now it's straightforward. Let's say I'm trying to find the output current here. What will be the contribution of this current to the output? Minus or plus? Minus. Okay, so it's minus, let's say, INM. So this current flows here, and now this current here, what do you think its contribution will be? It is same thing as we saw for the resistor case, so I'll write it like this. So it's same 1 plus GMRS. So finally, if you simplify, so if you simplify it, what do you get? So I simplify it, I'll have basically INRD plus I'll have RS that's scaled by GMRS by 1 plus GMRS, and I'll push it here. Plus due to the transistor, what is the ratio? Basically -1 plus this fraction, that becomes 1 by 1 plus GMRS. Okay. And the last thing pending is to find the transfer function from the input voltage to the output current. So let's do that. I'll short this guy. I out. So what do you think is the transfer function from I out by V in? No, first of all, it's dimensionally inconsistent, right? Again, assume R naught is infinity. If R naught is infinity, first of all, what can you say about this voltage Vx? It's basically the source follower configuration. Vx is times V in. And again, same, R naught is infinity, so whatever current flows here will flow through the transistor and go to the output. So what is I out? I out is basically Vx by Rs. That's all. So this boils down to Gm by, I mean, if you do it carefully, it is, we'll have a minus sign. Okay. So let's actually completely write the power spectral density, because I want to highlight us some points. So this is my I out, and my transfer function y is okay. So let's try to write the expression for the input referred voltage noise power spectral density. So what is that? Please help me write it. Due to RD, what is the contribution now? 4 kT by RD divided by this, let's say, y square. Okay. Due to RS, it's 4 kT by RS into this term whole square divided by this square. Yeah, so what happens? I mean, I have this square divided by this guy, so I'll just have RS. Okay. And last, due to the transistor, I have 4 kT gamma gm into this term square divided by this squared. Okay. So I'll basically have, let me write it maybe, GMR square right. So this simplifies to, I'll write it quickly. Okay. Now the interesting thing to notice, for at least for RS and transistor, things seem to be something simple. So let's try to make sense of it. We find that the input referred noise due to RS is simply 4 kT RS. Well, why does it make sense? If you look at the circuit, this was the circuit. Yeah, why does it make sense? Sorry? Okay, but my question is, why is the input referred noise due to resistor RS has a power spectral density 4 kT RS? Yeah, see, one thing is, we model the current due to the resistor using a parallel current source. How else can I model it? Can as well model it using a series voltage source. Okay, so I can do this also. And what is the power spectral density of this guy? 4 kT RS. And now you see that, I mean, for a transistor, all that matters is gate to source voltage. It doesn't matter if I have something here or something here, right? I'll basically, instead of this, I can also say that I have, at the gate, I have minus VN RS. I can as well say that this is the circuit, right? So now it's trivial. I mean, the input referred noise of this is already up there for you. It is simply VNRS, and that's why we have this guy. Okay. Now a similar thing happens for the transistor. So for that, let's understand this. See, if you have a MOSFET, the way we have modeled the noise is using a parallel current source like this, right? Say, let's say INM. And we know for a fact that if there is any noise at the output, we can refer it back to the input and model it as though it is coming from a voltage source and a current source. Now here the input is the gate of the MOSFET. So how many noise sources you need to model the output noise? One, which is just voltage. Okay. So instead of the noise being modeled at the output, I can say I have something like this. And what do you think the relation is between VNM and INM? It should be related by the transconductance. Okay, so this basically this times. Now I know for a fact the path spectral density of the current is 4 kT gamma gm. So what is the path spectral density of the voltage? 4 kT gamma by gm. Okay. So as long as, I mean, see, this is true as long as I don't consider the gate capacitances. Please remember that I can model the effect of the noise at the input using a voltage source only if my input impedance is infinite. Okay. And for MOSFET that is true if I don't consider the gate capacitances. So as long as I don't consider, let's say, CGS is neglected, I can say that the noise of MOSFET can be modeled like this. Okay, and this makes it very easy for us to calculate noise in all our op amps. Okay, and that's why you see that in the circuit that we had, instead of modeling the noise of the transistor using a current source like this, I can directly say that the noise of the transistor can be modeled using a series voltage source like this, and that directly gives me the input referred noise, right? Because our goal is to find the noise contribution due to each of the noisy elements and refer it back to an equivalent voltage source at the input, right? That's our whole goal. So now the way we have modeled the noise of the transistor is a voltage source at the input. So that's the effective input referred noise voltage. Is that clear? And again, mind that this is all okay as long as you don't consider CGS. The moment you have CGS, just modeling using a voltage source will not be sufficient. You'll also need to have some other current source here. And instead of doing that, you can as well model it using one current source at the output. So if you have gate capacitance, it's better to model the noise using a current source at the output, because then you'll have to deal with only one source. Right? But if there is no CGS, you can do this. Okay. So which means that in all our op amps, wherein the input is given to the gate of a MOSFET, and say the rest of the circuit is here. Now here if I try to find the input referred noise voltage due to each of the elements, what can you say about the noise contribution due to this transistor M1? If I try to find the input referred noise path spectral density, I'll have contribution due to each of the noisy elements. Due to this transistor M1, what can you say about the? It's simply 4 kT gamma by GM1. Okay, so we don't have to worry about it. Okay, again that's simply because I can model the noise of the transistor by a series voltage source like this. and that's exactly what you want also finally. Okay, cool. So let's do one more example and finish. So here I'll take an example of the Cascode. So this are Cascode amplifier. In, let's say it is some V bias. It's my output. On the top I'll assume we have an ideal current source I0. Okay, and again let's assume R0 for all the transistors is infinity. So please tell me the noise, input referred noise voltage. I'll label the transistors also M1, M2. What are the other results we got? And there should be some results, right? Find it. So due to M2 we have a case like this, right? I can basically do two things. I can model it using a current source, or for this transistor also I can model the noise using a series voltage source like this. Okay, anything is fine. So here I have assumed, I mean, what is the impedance looking down? I told R0 is infinity, so it's basically open. Okay, if this is basically open, if I call this current to be some IN2, what can you say about this current? That also has to be IN2, right? So this also IN2. So what about I out? 0. Okay, so you can do the same thing and try to show that even if you model it with voltage noise, this current, this is basically, I mean, okay, so this is even simpler, right? So what kind of circuit is this? Is it looking like a source follower? Basically this is like an ideal current source which has an infinite output resistance. So if I increment the voltage here by some delta V, what can you say about the increment here? Delta V, so basically no current flows. So I out is 0. Okay, so this is an interesting result. So SVN is basically 4 kT gamma by GM, and the Cascode device has no contribution to the noise. And why is it 0? What makes it 0? R0 of which transistor? Bottom. Okay, the reason is because this guy is open. So 0 noise if R01 is infinity. So let's quickly see what will happen if R0 is not infinity. So what do you think will happen if R01 is not infinity? Let's assume finite R01 alone. So here I am going to have something.
Result for that 4 kT gamma by GM will not change.
That will not change, right? That will not change. Okay, we can look carefully. So MOSFET, let's say I include R0 for the MOSFET. Okay, and I know that the current can be output, I mean the noise in the MOSFET can always be modeled like this. This is the fundamental model. Okay, so now if I try to find the input referred noise voltage for this guy, I'll be shorting the input, short the output. What will be the current flowing? So I out will be IN. Now this, let me finish it. So the second thing is to find the transfer function from the input to the output. Even if you have an R0, if I short this guy, if this is VN in, this current is GM VN in, and that current will entirely flow into the short circuit. So even if you have R0, it doesn't matter. The input referred noise voltage for a MOSFET is will have a pass spectral density 4 kT gamma by GM. Even if you have R0, it doesn't change. Okay, so let's come back to the issue of Cascode. So let's say now the bottom transistor has finite R0. Now, okay, let's model it using, okay, let's first do using current source. It's ground. So let's say this is IN2. Now how will you solve this? Yeah, basically now again you see that I have a similar case as before. I have a floating current source connected between two nodes. The simplest thing is to basically split it into two identical current sources. So So let me do that. Let us say this is one current source. Okay, and make sure that the directions are correct. Okay, if this is pointing down, this should also point down. That's the crucial thing. Say this IN2, IN2. What do you think the contribution due to this guy to I out is?
Minus IN2.
So I out will be minus IN2. Now you need to find the contribution due to this guy. It basically will be split between the impedance looking up and down. What is the impedance looking up?
1 by GM.
So what will be the division factor?
1 by GM.
No. It will be, what is the fraction? Yeah, okay, let's write it. R01 by R01 plus 1 by GM. This is GM2. Okay. Let's go. Yeah, so if I simplify it, what do we get? Okay. So this is basically the output, but I mean output noise. I'll also have to find the transfer function and divide it to get the input referred noise, right? So let's do that also. This is my transistor. Say we have an input referred noise. So this has a finite R0. So how can I find the output current? Yeah, so again, the current flowing here, we have a voltage controlled current source, and that will generate a current GM times VNN. Now this current again has to split between these two. So you'll have this is, let's say, GM1, right? So I'll probably have to make some space here. So what is I out? This is the current, and that has to split between the impedance looking down, which is R01, and the impedance looking up, which is 1 by GM2. So this will also be same, R01 by correct, right? Okay, so this is again GM1 VNN. Okay, so let's quickly write the complete transfer, input referred noise. So I out is IN2 by 1 plus GM2 R01, and the transfer function Y is GM1 times so what do you think VNN will be? What is the input referred noise voltage?
I have the point.
Yeah, so what is it?
1 is like 1.
So we'll have IN2. Now let's write the thing and then we can take the possible density. And then I have, or no, I think, okay, fine. So VNN, I'll write it here. VNN due to Cascode basically is INN by GM2. This is what we have. And remember, INN by GM2 is basically the input referred noise due to Cascode, right? Basically for the Cascode device, so you have to model the noise at the input of the Cascode device. This will be IN2 divided by GM2. It's not INN, sorry, this is IN2. Okay. Now this guy, when I refer it to the input, it seems to be divided by GM1 R01. Okay. So if I write the path spectral density, it will be 4 kT gamma by GM2. And that makes sense because I see if R0 is infinity, I will have 0 contribution. And with finite R0, you still have very small noise coming to it. So this is something this is one important property about Cascode. If you have Cascode, the noise is contributed only due to the main transistor, and the noise due to the Cascode device is actually divided by the gain of the main transistor. Okay, so let me write it. This is, let's say, MC for Cascode. This is M1. So noise of MC is divided by gain of M1 when you refer it to the input. So essentially the Cascode device doesn't contribute significantly to the noise at all. And that's a nice thing because you're getting a high gain, high output impedance, but the additional transistor is not adding any noise to you. It's kind of a win-win. But what is the issue with Cascode? What are you losing? Yeah, swing limit we are losing, right? Now we need to make sure both these guys have to be in saturation. So 2 times the overdrive voltage. Okay, so let's stop here and